Let me open the table of content first. Okay, we are still in chapter 20 here, patching smaller table, and still in the 20.3 section, multi-level page table, trying to understand how what is it called? How the structure, I guess, the structure of this multi-level page table. Let me open that. And one of the example that we take a look at. Okay, I hope my internet connection is stable enough. Well, let's see how it goes. Okay, we are in this section, multi-level page table, and the current example is we have two level page table. Here it is, two level page table. For the address space of size 16K and 64 byte page size. Okay, alright, maybe something like this. Wait, let me revisit my not that one. Okay, this one, I think, or maybe not. Maybe it is in this one. Okay, chapter 20. Oh, right. Okay, so let's say we have this address space size, right, with 16K address space size and 64 byte page size. Okay, and for byte page table entry. Okay, for the linear page table we have 256 page table entry. So I guess in this figure 20.4 it is something like this, a contiguous 256 item or entry, something like that. And then to create the two level page table, we need to divide the page table size, this linear page table size. And how do we get that? Basically, page table entry, right? The total of page table entry multiplied by the size of the page table entry. And what I mean by the size of the page table entry in here is that we what is it called? Is the information size, maybe something like that, is the size that one table entry store, something like that, the size of the table entry or the information that the table entry store. And in this case we have 4 bytes for each table entry, so 4 bytes of information for this each table entry or item, whatever you call it. Okay, so that's how we get the size of the page table. The total page table entry multiplied by the size of each entry. Okay, given that we have 64 byte page, the 1K page table can be divided into 64 byte page. And where do we get this number? Well, we divide that, the 1K divided by the 64, the page size. And 1K is the linear page table size, right? And the 64 is the page table page size. So each page in those page table have what is it called? 64 byte, something like that. This may sound confusing because some people might think that it is the same with the page table entry size or the entry size here, but it is not. I assume this entry size only storing, let's say, this kind of information, right? The address, what is it? The information about where the address is, something like that. So what is it called? We have this 4 byte table entry, but this one is the actual page that this address points to, maybe something like that. Okay, and then with the okay, that's how we got this 16. Okay, the 1K page table can be divided into 16 pages, right? Or in my term, I like to think of it like the small page table. So we have this big page table, the linear page table here, and then the small page table. So we divide the big page table by the small page table, and we got the 16 small page table, and each small page table can hold 16 entry, something like that. And we got that by dividing the total linear page table entry by the total small page table. That's how we got this 16 page table entry for each small page table. If I understand correctly, something like that. I think the previous figure is okay. In the figure 20.3 here, on the right side, multi-level page table, right? This one, this is the page directory. And inside of this page directory, we hold the reference for the small page table, like this one. This is the small page table, and it is only valid when at least one table entry in the small page table is valid, like this one. Okay, this is the small page table 1, only one invalid here, and then this is the small page table 2, and 2 invalid here, but the rest of the address is valid, right? That's why we have that in the page directory. So instead of one contiguous memory like this, like the linear one, right, side by side, we can place this depending on the valid or not. I mean, if if it is invalid, we didn't allocate any memory for it, something like that. Okay, this is the illustration of dividing this contiguous or linear page table into the small page table. And if we take a look at the previous example on chapter 18, I guess, see, in this in this chapter 18, we have the address space size 16K and the page size 1K. So its page table entry, have the range of 1K, something like that. So address 0 until address 1023, and then when we have this page table entry 1, the base address is the 1024 until 2047. So its table entry here have the range, right? This is the linear page table, and yeah, that's why I think of it like the small page table, because the table entry from the linear here become its own table, become its own page table, right? Okay, this is the page frame number. So there is this index in the linear page table, right? Virtual page number, the VPN, and its index, or maybe its entry. Yeah, I'm still not sure. Can we call the virtual page number as the page table entry? Maybe not. I mean, from what I understand, virtual page number is the index, like this one, at least from the chapter 18. But what about the page table entry? Maybe it is the same. We don't really talk that in the chapter 18 maybe I didn't take notes of it. That can also happen. Okay, page table entry. Wait a minute, let me check. 18-bit virtual page number, assuming the same size for each page table entry. Oh, okay. Maybe it is different. The virtual page number here is the index, like this one, 0, 1, 2, 3, 4, until 15 in this case. This is the virtual page number, and maybe the entry is this address. Maybe. I mean, we have 256 entry, right, from this example. Where is it? Yeah, from this example we have 256 entries. Okay, so maybe virtual page number VPN is the page table index, and then the table entry or PTA is the address, I guess. Address inside the VPN, the virtual page number. Maybe something like that. Okay, if that is the case, then for each, what is it called, virtual page number, well, in this case it is page frame number, we create the table. Okay, where is it? It's page directory. Thus all we need to figure out is how to construct the index for each page directory from pages of the virtual page number. Let me check this. Store only. Okay. Is the page table index? Okay. Only. Page table index, I guess this has at least one valid address. Okay. That has at least one valid address. The page table size is equal to page size. I mean, we are chopping this up, right? From this linear page table into, in this case, I guess two level page table. Okay, so we are storing the index, the valid index in the page directory, and then this is the page table entry for those index, like this. Maybe something like that. The page table size is equal to page size. So unlike linear page table where we have one big page table with page table entry inside of it, in multi-level page table we treat its page table entry as its own page table. No, I don't think this is page table entry. With page table entry inside of it. Okay, its page table index as its own page table and store the page table index that has at least and store the page table index that has at least one valid address in the page directory. Page table index in here means something like virtual page number or page frame number, PFN. Okay, so yeah, maybe that's why it is called page 10, page 9, maybe something like that. And inside those pages we have this page table entry. Or PFN is one page, maybe something like that. One page, and inside those pages we have page entry, the PTA. Maybe something like this. Yeah, I'm making hypothesis, I guess. I'm not sure if this is correct or not. So its virtual page number or page frame number is one page, and inside those pages we have Inside those page we have page table entry. Maybe that is the relation here. Okay. We treat its page table index. Yeah, let me put this in here. PN or PFN is one page, and inside those page we have page table entry. We have page table entry. Okay. Okay. And then put this here maybe. Page table entry is the address inside the virtual page number. Okay. We have page table entry. Alright. And store the page table index that has at least one valid address in the page directory. One valid PTA, maybe something like that. I'm still not sure. We don't need to have contiguous memory to store the page table. Okay. Okay. Oh, hello, ping pong poing. Welcome. Yeah, we are continuing on chapter 20 here. Still trying to figure out about the multi-level page table concept. Okay. Yeah, by analyzing this figure 20.3, yeah, I'm trying to understand which one is the page table entry and which one is the index, I guess. Okay. And for now, I assume this is the index and this is the entry to those index, and each of this index is, what is it called? Each of this index each of this index is one page. So the range of the entry, right? The range of the entry here depends on the page size. I assume something like that. Okay. Okay, the range. We have page table entry. Okay. And how many PTA we have in one page? In one page depends on the page size. Maybe depends on the page size. Maybe something like that. I mean, in this example, right? Chapter 18 example, we have address space 16K and page size 1K. And if we divide that $16. Oh, this is 16 and 3. I'm still kind of confused about what is the entry and what is the index here. Maybe this is not the total page table entry. Maybe, but the total page. And then the total page multiplied by page table entry size. And again, with my previous assumption, right? Where is it? Virtual page number or page frame number is one page, and inside those pages we have page table entry. So maybe this is not the total page table entry, but the total page. Maybe total page, virtual page number or PFN, the page frame number, and then this one is page, total page, multiplied by the page table entry size. So each of these page have what is it called? Each of these page contain the entry, I guess. Contain the information about the table entry. inner page table size. Divide by page size. Okay. Total page divide by total to level page directory entry inside each PTA. Okay, so maybe the page directory only store the page table index, or only store the each page, I guess. So in this case we have maybe 16 pages, something like that, and inside the 16 page we have entry, let's say 0 until 1023. What is it? Let's say we have address space size 16k here and page size 1k. We have 16 pages, right? With each page contains 1024 entries. Maybe something like this. With each page contains 1024 entries. Right. Maybe. So in this case, a page directory is an array of entries. Thus all we need to figure out is how to construct the index for each page directory from pieces of the virtual page number. I think this is from one of the statement. Where is it? I think before this one. Okay. Is page directory. Okay. Oh, it's array of entries. Okay. Remember that it's I'm not sure what it's in this refer to. For now I'm assuming this is refer to the page directory. So remember that each page directory is an array of entries. Thus all we need to figure out is how to construct the index for each page directory from pieces of the virtual page number. Index for each page directory from pieces of the virtual page number. I mean, the illustration using the base directory index, right? Let's first index into the base directory. Our base table in this example is small, 256 entry, spread across 16 pages. Oh, it is entries. Let me check. Page 64. Okay, this is entry. Spread across 16 pages. Spread across 16 pages. The base directory needs one entry per page of the base table. Per page of the base table. Thus it has 16 entries. As a result, we need 4 pages. Okay. 256 entries spread across 16 pages. The base directory needs one entry per page. One entry per page of the page table. One entry per page of the page table. Thus it has 16 entries. So from this 16 pages, one page from the 16 pages have 16 entries. I think something like this. Okay. So if we take a look at this figure 20.3, right? I assume this is the, what is it called? The 256 entry in the previous example. And then each of this entry need, oh wait, no, this is the 16 page, right? So imagine the page directory is 16 pages, and then each page have 16 entry, 16 page table entry, maybe something like that. But yeah, in this what is it called? In this figure example, we have, what is it? 4. Okay, 1, 2, 3, 4. Oh, we have, I guess 16. Yeah, what is the entry here? Yeah, in this example, I guess we have 16 pages. Oh, I mean 16 entries, right? 16 page table entry, which is in, what is it called, in 4 page, spread across 4 page. Let me figure. We have 16 page table entry spread across 4 page. The virtual page number or page frame number, right? This is the linear, the multi-level, is we have page directory that contains the page, I guess. Contains 4 pages and each page contains 4 PTA, 4 page table entry. So the total is that we still have 16 page table entry. Wait. I think so, right? We still have 16 page table entry. But we divide that into 2 level, I guess. It's like we divide this page table entry by 2. Oh no, that's not right. Again, see, if it is divided by 2, it should be 8. No. Not really divided by 2, but yeah, divided by the actual page that we use. And how do we get this page? How do we get this page? By, I guess, divide the address space. Yeah, that make me curious. Is dividing the address space by page size result in page table entry or the page, the total page? Is dividing page size with page size result in, what is it, page table entry or total page, the virtual page number or PFN. this case, right? No, not that one. This one, we got 16. And my illustration is something like this, right? So maybe dividing the space size here by the page size result in the total page instead of the page table entry. And but to get the page table entry, yeah, that make me wonder how to get the page table entry. Is it the yeah, maybe the is page table entry or the PTAN total page number or PFN the same or not? That's what I'm wondering. Is the page table entry and the total page the same or not? Maybe something like this. Okay. If this is the page table entry, then how do we get this one? I mean, from this diagram, I assume that we have the page size of 4 byte here. Page size 4 byte with the address space 16 byte maybe. Assumption. Okay, yeah. Wait. Assumption. We have page size 4 bytes and what is it? The page no. Page size 4 byte with the 16 bytes address space question mark. We have page size 4 byte and 16 byte address space. Maybe and that's why we have this 4 pages, right? 16 divided by 4, so each page here have what is it, 4 entry, something like that. Is there any information? A developer doesn't rely on segmentation but attack the same problem. How to get rid of all those invalid regions in the page table instead of keeping them all in memory. We call this approach a multi-level page table, as it turns the linear page table into something like a tree. This approach is so effective that many modern systems employ it. Okay. First, we chop up the page table into page size unit. Then, if an entire page of page table entries PTA is invalid, don't allocate that page of the page table at all. To track whether a page of the page table is valid, use a new structure called the page directory. A page of the page table. A page of the page table. Okay, so I assume this is the page of the page table, right? The entire page of the page table, right? And I assume this page of the page table, or the entire page of the test table, is the entry inside those pages. Maybe something like that. Okay, on the left of the figure is the classic linear page table. Even though most of the middle region of the address space are not valid. Okay. The page directory. Oh, wait a minute. If my assumption here is correct about the figure 2.3, okay, assumption to left, okay, no, yeah, if my assumption for figure 2.3 in here correct, right, figure 20.3, then what is it called? The page table entry is the address space, I guess, and then this one, the index, or the page frame number, or if the virtual site, it is the virtual page number, is the page. Okay, maybe something like that. A linear page table would have 256. Yet, I mean, it's kind of confusing when we use the same term, you know. Where is it? I think no, maybe this one. Our page table in this example is small, 256 entries spread across 16 pages, and then we are using this term entries again. Is this the same or different? Right. The page directory needs one entry per page of the page table. Right. Spread across 16 pages. Okay. Spread across 16 pages. So I assume, right? Okay. Spread across 4 pages. Okay. We have page directory that contains 4 pages, and each page contains 4 page table entry. Maybe let's revisit the chapter 18 again. Let's see. Okay. Is there any explanation about page table entry? Looks up the page table entry at that index. In order to find the desired physical frame number. At that index. Okay. So maybe this is actually the page, right? Maybe, and each of these pages contain 4 page table entry. But then, okay, maybe this mean in this case, right? Address space size 16K with 64 byte bits. Okay, we have 14-bit virtual address space, 8-bit for the virtual base number, and 6-bit for the offset. The offset is from this bit size, and then this 14-bit is the exponent for the 16k here, and the 8 bits is, well, we divide this by this, so we have this, right? And it looks like this is the page. A linear page table have 256 pages. Okay. So imagine this figure 20.3, right? This one, but instead of 16, right, we have instead of 4, instead of 4 like this, we have 256 of this page frame number, or virtual page number, I guess. We have that, right? We have 256 pages for the linear page table, even if only a small portion of the address space is in use. And that kind of interesting. We didn't divide anything yet in this figure 20.3. Okay, maybe we haven't what is it called? We haven't considering about what is it? Its entry size, like what we store, what kind of information in this entry that we store. Maybe the valid bit or something like that, right? Okay. With that in mind, we got the page table size, right? 256 pages multiplied by 4 byte. In this case, yeah, each page table entry contain 4 byte of information, something like that. So we multiply the total page by the page table entry size. Let me check. Total page, okay. Total page multiplied by page table entry size. Okay. Yeah, maybe I need to explain this one. Page table entry size. Where should I explain this? Maybe this one is the size of its size of information in its page entries. Yeah, maybe something like this. Is the size of information its page entry. Okay, total page, total to level page directory entry. Well, let me continue this first. Okay, given that we have 64 byte page for byte page, okay, the 1K page table can be divided into 64 byte page. Each page can hold 16 page table entry. Okay, so from this total page, the linear total page, I guess, we divide that again by the page table, by the page size, I mean, linear page table size, divide by page size, and then we got the page directory entry. Yeah, maybe we can call that entry the page directory entry. Okay, and then the total page, and then to get the page table entry inside each of the page directory entry, we divide the total page by total to level page directory entry and get this one. Each page can hold 16 page table entry. Okay, so that's why it is called page, not page directory, not page table entry, because this one is also total page. Okay, the entry is, I assume, the address size, maybe something like that. Okay, so maybe we can imagine the page size here as the grouping category, like we are grouping, what is it called? We are grouping the entry within those address space size, right? Within this address space, we are grouping by 16 for byte, 16 for byte, 16 for byte. Maybe something like that. We are grouping that per page, right? And then inside those grouping page, we divide that again into different table, I guess, something like that. So instead of having one big page table, we have in this case two page table the one who store the page, right? Maybe the index page, and the one who store the page table entry. Maybe something like that. What we need to understand now is how to take a virtual page number and use it to index first into the page directory and then into the page of the page table. Into the page of the page table. Yeah, I assume this is the entry, what is it? The page entry, right? And we have the address size, the address space, total of this entry. Okay. To take a virtual page number and use it to index first. Okay, so we take the page, right? The page index from this virtual page number and use it to index first into the page directory and then into the page of the page table. Okay, page of the page table. If I understand correctly, this page of the page table is one of the actual page here. Maybe. Okay. So we have a small page, smaller page, right? And then one of the smaller page will be a reference to a larger page. Is that correct? I'm not sure. Use it to index first into the page directory and then into the page of the page table. Page of the page table here. So we have one page. Page of the page table. Okay. Page directory here. Yeah, let me check this again. The page directory in a simple two-level table contains one entry per page of the page table. One entry per page of the page table. It consists of a number of page directory entries. Consists of a number of page directory entries. Similar to a page table entry. Contains one entry per page of the page table. I assume this one entry per page of the page table. Yeah, the page of the page table may be this page from the linear page table, maybe something like that. Thus all we need to figure out is how to construct the index. And then into the page of the page table. Okay, we need to have the page directory index, and then going into one of these 256 page, and then from that we go into the page table entry. Remember that it's what it's in this we're talking about. Its page directory is an array of entries, or maybe it's page of the page table. Remember that each page of the page table is an array of entries. Thus all we need to figure out is how to construct the index for each page from pieces of the virtual page number. I still think page directory here fit better, I guess. Remember that each page directory is an array of entries. Thus all we need to figure out is how to construct the index for each page directory from pieces of the virtual page number. Something like that. Oh, Bim Bom Boing said, don't forget to take rest and drink water. Also eat breakfast, alright. Yeah, let me drink some water first. Don't forget to drink water. Thus all we need to figure out is how to construct the index for each page directory from pieces of the virtual page number. Yeah, maybe it's in this case means page directory. We will see. Let's first index into the page directory. Our page table in this example is small. We have 256 pages split across 16 small pages, maybe something like that. Split across 16 small pages. The page directory needs one entry per small page, I guess. Oh, no. the page directory needs one entry. Need one entry per page of the page table. This one, I guess. Thus it has 16 entries. It has 16 entries, so one page directory entry needs, okay, the page directory needs one entry per page of the page table, per page of the page table. Page directory needs one entry. Need one entry per page of the page table. Thus it has 16 entry. So let's say that we have okay 256 page, right? This is spread across 16 page directory entries, maybe something like this. And each of these page directory entries, we have the 16 page table entries. Each PTA has or have 16 page table entries. Yeah, maybe something like this. I mean, again, if we do this, right, it's 256 bits. It's an array of entries. Is page directory, yeah, maybe this is PTA, the page directory entry. Each page directory entry is an array of entries. So one page directory entry, like figure 20.3 here, this entry, right, is an array of page table entry. I assume something like that. Contains one entry per page of the page table. The page directory in a simple two-level table contains one entry. page of the page table. Yeah, and then the page of the page table is this one. The page frame number or the virtual page number. Okay. It consists of a number of page directory entries. Okay, a PTA minimally has valid bit. Okay, if the PTA is valid, it means at least one of the pages of the page table that the entry points to via the page frame number is valid. That is in at least one PTA on that page pointed to by this page directory entry. The valid bit in that PTA is set to 1. Okay. So maybe array of PTA, array of page table entry. Thus all we need to figure out is how to construct an index for each. For each PTA from pieces of the virtual page number. Maybe something like this. So one page directory entry contains an array of page table entry. One PTA contains page of the page table. I assume this is the page table entry. Maybe something like this. Oh wait, no. That at least one of the page table. Okay, so this is quite interesting. I mean, in a simple truth level table, right? We only have one page of the page table here. Only one. But maybe in more than 2 level page table, we have multiple pages from this page table. Okay. Alright. Contains the of page table. Array of entries. Array of entries. Where is it? Our page table in this example. Is an array of entries. Or maybe this one. Each page of the page table. But No, I don't think that is correct. Is page directory? Yeah, maybe. You know what? Maybe this is correct. Is page directory is an array of entries or PTA. Maybe something like that. How to take a virtual page number and use it to index first into the page directory and then into the page of the page table. Remember that each is an array of entries. Thus all we need to figure out is how to construct the index for each page directory from pieces of the virtual page number. Okay, so maybe something like this: the directory, and then there is what is it called? Directory 1, and then page table index. Okay, page 1 maybe something like that, and then entry 1, and then there's also this entry 2, right? And then entry 3 maybe, and then we might also have page 2. So page directory 1 but with page 2 and then the entry 1. Maybe something like that. Contains the page of the page table. Page directory. An array of entries. Thus all we need to figure out is how to construct the index for each page directory. I assume these entries means the page directory entry. Construct the index for each page directory from pieces of the virtual page number. Yeah, this can, the entry in this can mean PTA or PTA, the page table entry. But if my assumption here is correct, I mean for now we only have 2 level page table, right? Where is it? In a simple 2-level table contains 1 entry per page of the page table. It consists of a number of the page directory entry. PTA minimally, okay. Alright. Page of the page table. Page of the page table. We need to understand this. So it's not it's 4 byte SPTA. Our page table in this example is small, okay. Split across 16 pages. SMR. Okay. The page directory needs one entry per page of the page table. Thus it has 16 entry. Yeah, I need to understand this. How do I explain this? Page of the page table. I mean, from the illustration here, it is easy to understand, I guess. But how do you explain this? Page of the page table. I mean, again, we use a lot of the term page for different what is it called? For different scenario. Okay, like this one. Split across 16 pages. And then this is page of page table. Isn't this 16 pages also page of the page table? Right? See, it's getting confusing, at least for me. Yeah. What is page of the page table? Let's try answering this question. On the next session, I guess. So that's it for now. Thank you for watching and see you next time. Bye bye.